Good evening. It's so nice to see everyone here tonight. Thank you for coming. I'm Michelle Larson. I'm the president and CEO of the Adler Planetarium. So welcome to our house. We're delighted to have you here for our Kavli Full Dome lecture this evening. Tonight you're going to go on an adventure of frontier visualization techniques to really put on the dome excellent visuals that are going to help tell the story that we are going to hear, and then also frontier science. And so you're going to have that combination of hearing what Dan Schrag, our speaker, is researching and seeing what he's researching because you're sitting under our wonderful dome in the Granger Sky Theater. In addition to the frontier science and the frontier visualizations, we are also pioneering a technique of pushing out this lecture live all across the globe so that planetaria around the world can participate and hear from Dr. Schrag and see the same visuals that you will be seeing. So in the combination of this afternoon's noon lecture, which could hit time zones different from this evening's 7:30 lecture, the two lectures together have been broadcast in 17 cities, in 6 countries, and on 4 continents. So it's really wonderful to be able to reach that many people. Thank you. The Adler Planetarium is committed to reaching people where they are and connecting them with the sky. So in addition to all of those planetarium domes that I just articulated, we are also live broadcasting this lecture to YouTube 360. And participants that cannot make it to a planetarium dome can use their smartphone together with like a cardboard viewer. Google Cardboard is one of the most popular. And they can put that on their face, and while we're watching the lecture tonight, they will be looking around the dome just like you are in virtual reality through YouTube 360. So we have children at Lurie Children's Hospital and in rural communities across the country that don't have access to a planetarium. So we're very excited to be able to offer that to you here in the room and also to offer that all around the world. How did we do this? How is this all made possible? Well, it's made possible by our wonderful sponsor, the Kavli Foundation. And so this was dreamed up about 5 years ago, and our first lecture was 3 years ago, and so we are now experiencing the 5th Full Dome lecture sponsored by the Kavli Foundation. Jim Cohen is here in the back. He flew in today from California from the Kavli Foundation to experience this with us. But Jim, we're just so appreciative of you sharing our vision for what this could be. These are our Adler teens and other members that are coming in, so welcome everybody. The Kavli Foundation also has a mission to advance science. So it is a foundation that funds science in astrophysics and in other areas, but then they also have a commitment to increasing awareness of frontier science. And I think that's part of the reason why this has made such a great partnership, because we are trying to teach you about the frontier and make you aware of what's going on. So finally, I just want to mention that we are hearing tonight from Dr. Daniel Schrag. Dr. Schrag is the Sturgis Hooper Professor of Geology, Environmental Science, and Engineering at Harvard University. He's also the director of the Harvard University Center for the Environment. Dr. Schrag is going to teach us tonight about what we can learn about our own planet and the evolution that our own planet is going through by looking at ourselves and other planets in the solar system. So as you know, the title of tonight's talk is Our Planetary Experiment, and it is a way for us to reflect on what's happening and think about what could happen based on data that we can gather in other places. So please join me in welcoming Dr. Dan Schrag for tonight's lecture.
Thank you, Michelle. Thank you all for coming tonight. And thank you to the Kavli Foundation for actually inviting me to do this. This is really exciting for me. What you're going to see tonight actually took a whole team of people to create. And this amazing team at the Adler Planetarium has been working really since January to put this together. And so they deserve a huge round of applause. But in particular, there's one person, Mark Subarau, who's in the middle there driving the controls. And Mark, let's give Mark a round of applause. Mark actually created the graphics that you're going to see tonight, along with some of his colleagues, but he really has been my partner in conceiving and creating this show. Now, I'll tell you something. I'll tell you a secret that I didn't tell the Noon group, which is until I came to the Adler in January for the first time, I actually hadn't been in a planetarium since I was about 9 years old. I think it was my 9th or 10th birthday party I had in New York City at the Hayden Planetarium, and I don't think I've returned to one since. I am the first non-astronomer to give this Kavli lecture, and it was a really interesting challenge. Because what a spectacular environment, but how to think about the Earth using a dome. It's really easy if you're an astronomer, right? You just show the stars. But how do you actually tell a story using the visual capability that we're in if you're an Earth scientist? It's an interesting challenge. I actually think this could get more and more interesting as virtual reality permeates society, and people don't need domes to see this, but this is an incredible opportunity. I will tell you that I get dizzy when we move around space, so there may be some times in the show where I'm actually going to just anchor myself, and that's because if I don't, I might fall over as we're talking. Okay, so what I want to talk to you about tonight is our planetary experiment. We're going to be talking about the Earth, and we're going to be talking about climate change. And I'm going to describe it as an experiment because it's kind of extraordinary. I want to use the context of other planets in the solar system and Earth history to give you a little bit of perspective of how I think about climate change as a geologist. So there's the Earth. We're zooming in on it from space. You know, it's our planet, and it's an extraordinary planet in many, many different ways. And I want you to appreciate some of the processes that have controlled its evolution over time. But I want to start out doing something a little bit interesting. We're going to fly in to the surface of the Earth, and we're going to actually land. There you see the Great Lakes. And we're going to come down, and we're going to actually land not too far from here, just a little bit north of here, a place in Illinois near the Wisconsin border. And what you see, this is an industrial scene, not too far from here, as I said. And you see, that's a coal plant right there. There's steam coming out of that smokestack. What you don't see coming out of that smokestack is carbon dioxide. Now, carbon dioxide is a gas that is common in the Earth's atmosphere. We breathe it out. We breathe in air, and what goes out of our bodies is carbon dioxide that comes from respiration of food that we eat. But because of burning of fossil fuels, essentially taking carbon that was made by plants millions, sometimes hundreds of millions of years ago, and then stored underground away from the atmosphere, we've started over the last 150 years of the Industrial Revolution to start using those fossil fuels and burning them for energy and putting that carbon dioxide back in the atmosphere. And essentially, we're doing it so quickly that we're making a profound difference in the atmosphere. And what I want to do today is just give you a perspective on that I have as a geologist. Now, before we do that, Mark and I dreamed up an interesting way of experiencing this change in carbon dioxide, because carbon dioxide is invisible. We thought, you know, if you could actually see carbon dioxide, maybe you would think about this problem a little differently. So we're going to try that experiment. What if carbon dioxide had a color? Imagine carbon dioxide was red. There it is. If you look around now, you'll see it's no longer a bright blue sky. It's kind of got a purplish tint. You can see the bright scarlet stream of carbon dioxide coming out of that smokestack. Right? But how do we think about the changes in the Earth's atmosphere? Surely the atmosphere is big enough to absorb a little bit of carbon dioxide. Well, imagine the year is 1958. That's where we're going to start this story. And the reason that's an important year is that's the year that Charles David Keeling, most of us call Dave Keeling, started measuring atmospheric carbon dioxide in the top of a volcano in Mauna Loa, Hawaii. Now, why did he do it on top of a volcano? Well, it turns out on top of Mauna Loa is a good place because he was trying to get far away from the surface of the Earth where there's lots of cars and industrial activity, and going out to Hawaii where you're out in the middle of the Pacific, and if you're up at high altitude, the winds are coming off the Ocean, he thought this was a good place to sort of measure the average background level in the northern hemisphere. And he measured it, and he got a number of 315 parts per million. That was kind of interesting. He wasn't quite sure he got it right because when he made subsequent measurements, it turns out that they weren't quite the same. They actually went up a little bit, and then they came down a little bit. And then they went back up a little bit, and then they came down a little bit. And it was after a couple of years that he realized this isn't a problem with the measurement. We're actually seeing changes in the carbon dioxide of the atmosphere. This is the Earth breathing. The northern hemisphere is where most of the landmass is on the surface of the Earth. And in the spring and summer, plants grow. They make leaves, they make their organic matter, and take carbon dioxide up out of the atmosphere. And carbon dioxide drops. And then in the fall and in the winter, bacteria and fungi eat that organic matter and respire it and turn it back into carbon dioxide, and so the carbon dioxide comes back up. And so what he was seeing was just the northern hemisphere breathing carbon in the spring and summer and releasing it in the fall and winter. But he kept measuring CO2. People sort of said, well, aren't you done? You know, you got the answer. And what's interesting is, after he measured it for about 5 or 6 years, he realized that it was changing. It was slowly going up. Now, 100 years ago, more than 100 years ago, we already knew that carbon dioxide was a greenhouse gas. The physics of it is actually pretty simple. Carbon dioxide absorbs infrared radiation, which is what we think of as heat. And so we knew that carbon dioxide in the atmosphere was partly what keeps our climate warm. And people had already predicted that burning fossil fuels would someday change the carbon dioxide content of the atmosphere. But when Dave Keeling started seeing carbon dioxide rising year after year after year, he realized that we had really identified the human impact on the atmosphere. And we know from the isotopes of carbon in that carbon dioxide that the source of this is the fossil fuel that we burn, the coal, the oil, the gas. So he kept going past 1965. He measured it year after year after year. And what he saw in the 1970s and then the 1980s, 1990s, Dave Keeling died in 2005 when CO2 was 380 parts per million. But his son, Ralph, continued to measure carbon dioxide. And then just last week, Ralph Keeling reported the first measurement above 410 parts per million. Kind of extraordinary. A family legacy. You can see at 410 parts per million, we're no longer just a subtle shade of purple. We're getting quite purple in the atmosphere. But this graph doesn't tell the whole story. I think about this as a geologist. I think about longer periods of time. So what I want to do is actually take you back even further. I want to go back long before the Industrial Revolution. I want to go back 400,000 years ago. 400,000 years ago, the atmospheric carbon dioxide was about 280 parts per million. So far lower than it is today. It's about the same level that it was at the beginning of the Industrial Revolution, before we started using all of the fossil fuels for energy. Okay? What I want to show you is what happened to the Earth over this time scale. What you see there is part of the northern hemisphere with the US in the center. And watch what happens as carbon dioxide changes over time. These measurements come from ice core. This is the Vostok ice core from Antarctica. Goes back 400,000 years. And so these are carbon dioxide measurements of bubbles of air trapped in the ice. We can measure those and tell us what CO2 was. You can see the ice sheets advancing when carbon dioxide drops and then receding when carbon dioxide goes up. These low points, the glacial maxima, when the ice sheets are at their largest, are timed with CO2 levels around 180 parts per million. And the glacial minima, what we call interglacials, are with CO2 levels around 280 parts per million. And you can see that fluctuation. You can see the ice coming down to Chicago, where I live in Boston, would be under about 1 kilometer of ice. Temperature change was about 5 degrees Celsius. And sea level, during the last glacial maximum 20,000 years ago, we're coming to it in just a few seconds, was about 130 meters lower than today, about 400 feet lower. So there's the glacial maximum coming. And what you'll see then is a retreat that actually seems very quick on this time scale, but in fact that deglaciation took about 10,000 years. And then here we are in the pre-industrial period at 1850, okay, 1849. And then we started burning fossil fuels and human population increased. It brought lots of prosperity, lots of wonderful things to the world, but it did change the atmosphere. And to me, this is the proper context to view the Keeling curve. So let's now see the Keeling curve on this time scale. In just 150 years, we now are at 410 parts per million. What can we say about this? Well, we know for certain that carbon dioxide levels have never been above 300 parts per million for at least now the last 800,000 years. This is just 400,000, but we have other ice cores that go back even further. And indirectly, we think that CO2 levels haven't been this high for probably 3 or 4 million years. So this is really an extraordinary experiment we're doing. And by the way, at the current rate of increase, which is about 10 ppm every 4 years, by 2054, we will see levels that are about 500 parts per million. That's guaranteed. The question is, how high will we go? Will we see 600? I think that's pretty likely. 700? I think that's pretty likely too, unfortunately. 900? 1200? That's the question that we're going to talk about today. And what does that actually mean for the Earth system? But you can see the Earth is getting pretty red. Now, I have an admission to make. When Mark and I dreamed up this idea of seeing CO2, we thought it was kind of original. It turns out that there was a NASA team that actually had this idea completely independently. And so we learned that it wasn't such a completely original idea. This is an awesome NASA visualization of carbon dioxide mixing in the northern hemisphere. It's very different because what they were trying to show was the winds and the pattern of circulation in the atmosphere that mixes carbon dioxide from industrial sources around the northern hemisphere. And so this was an image that they did for essentially the northern hemisphere winter, when the southern hemisphere is a little lower, and the scale is such that you don't see carbon dioxide levels much below the average, and what you see on the high level is just, the very bright red. That's just 5 or 10 ppm higher. So the scale is very, very exaggerated here, but it's kind of awesome to see the mixing of the carbon dioxide in the atmosphere and watch how the air currents essentially mix the sources of carbon dioxide around the northern hemisphere. It's really a spectacular image. Okay, let's move on. So this is our planet. This is the experiment we're doing with the planet. And what I want to do is compare this to our neighboring planets and think a little bit about the evolution of the planetary system. But before we do that, we all have to go to school. So I know this is not just going to be a lecture showing beautiful pictures of space. There's going to be the next 2 or 3 minutes is going to be a short lesson in geochemistry. So this is our Earth, but now sort of a Monty Python version of the Earth. I think that's kind of fun. You see this volcano in the middle with scarlet carbon dioxide coming out. You see the smokestacks in the back there. Why is the volcano there? Right? This is not the big island of Hawaii that's erupting right now. Well, it turns out that on long geologic periods of time, carbon dioxide emissions from volcanoes are really important for the climate. Let me be very clear. The amount of carbon dioxide coming out of volcanoes is not that significant on human timescales. It's about 1% of what we burn every year in fossil fuels. Okay, so it's not that big a deal. But it's persistent. It keeps going over geologic time. And so if you allowed volcanoes to just emit CO2 continued for thousands of years, for tens of thousands of years, for hundreds of thousands of years, the sky would get redder and redder and redder. Carbon dioxide would build up, and we'd have an ultra greenhouse climate, and we'd boil. Right? That would not be so good. It turns out the Earth has a natural system for dealing with this, a simple chemical reaction that many chemists don't appreciate. It's just a simple acid-base reaction. And it's based on the fact that when carbon dioxide dissolves in water, it actually forms an acid, carbonic acid, what we call seltzer. Right? So if we have a little rain, here's the rain coming. You thought you were going to avoid the rain outside, but there's our rain, and you can see the rain falling, and basically the carbon dioxide forms carbonic acid as it mixes with the rainwater, and when it falls on the Earth's surface, it reacts with rocks on the Earth's surface. Now these are rocks that are formed from magmas, so these are igneous rocks on the Earth's surface, and when the carbonic acid hits these rocks, there's a chemical reaction that occurs, and the carbonic acid is neutralized. It forms other minerals we call clay minerals, and the solutes, the chemicals, are washed down from the rivers into the ocean and ultimately precipitate on the ocean floor as a new mineral called calcium carbonate. That's essentially chalk or limestone, what clams or corals make their shells out of. And so you see the calcium carbonate forming on the ocean floor in red, and what happens is, as that happens, carbon dioxide is pulled out of the atmosphere, and so it's no longer quite so purple. Okay? But here's the interesting thing about this chemical reaction, and then this is where the lesson stops. That chemical reaction is dependent on temperature and on climate in general. If the Earth ever gets too warm, the reaction speeds up, and more carbon dioxide is pulled out of the atmosphere. If the Earth ever gets too cold, that reaction slows down, and volcanoes continue to put CO2 into the atmosphere, higher and higher levels, and the climate is restored. So this simple chemical reaction between carbon dioxide, water, and rock is actually a thermostat for the Earth. It's not a thermostat like the one in your house. It doesn't set the temperature to be exactly 72 degrees. But it does, over a timescale of tens of thousands to 100,000 years, make sure that the climate doesn't get too out of control. Now, it turns out that there's a nice example of this at a time when the climate did actually get pretty far out of control. And this is something we call the Snowball Earth. So we're going to come back to the Earth now, but now this is what the Earth might have looked like 700 million years ago. This is an artistic example where you see all the continents in one continent, all near the equator. This is not necessarily geologically accurate, but it serves the purpose for this demonstration. So what's interesting about the climate of the Earth is that it's regulated by energy from the sun. So it's sunlight that actually warms the surface. The visible light from the sun gets absorbed by the surface and turns into heat, which then is emitted back to space. So there's an energy balance. Now, it turns out that if this climate ever started to cool, you would see little ice sheets appear near the poles, and it would have an interesting effect on the climate. Many, many years ago, climate scientists realized that the reflectivity of ice actually had a very interesting effect on the climate. Because now, because of that high latitude ice sheet, more sunlight is being reflected back to space. Therefore, the Earth is colder than it would have been. So the ice sheet actually stabilizes itself just by reflecting sunlight back to space and cooling the Earth a little bit. But I think you can all see that a tiny little ice sheet, in this case sea ice, up at the pole doesn't do much. First, it doesn't cover that much area of the Earth. And second, it's at high latitude where there's not that much direct sunlight. But if the ice actually ever extended further, if the Earth got colder and colder, and the ice extended down towards the equator, what you can see is that the surface area the ice covers becomes greater, and also the sunlight becomes much more direct. And so the effect of that high reflectivity of the ice becomes really important. It was interesting, a Soviet scientist, a Russian scientist named Mikhail Budyko was one of the first people to explore this. He was actually working with the Soviet military in the 1950s, thinking about nuclear winter. So he was thinking about what would happen if we set off lots of thermonuclear devices, and he was playing with early climate models, and he realized that what would happen if the ice ever got past about 30 degrees north and south, the effect of this extra reflection of sunlight would be so great that it would actually freeze over completely, and the entire Earth would very quickly become a snowball. And Mikhail Budyko said, you know, this obviously never happened in Earth history. This never happened because it's so stable. Temperature would plummet to about minus 50 degrees Celsius. And it's so stable that it would stay that way forever. Of course, Mikhail Budyko didn't understand something that you already know. So what would happen to this chemical reaction between carbon dioxide, water, and rock if the Earth ever froze over? Well, it would obviously slow down or essentially stop. But do volcanoes care about the surface temperature? No. Volcanoes are driven by the internal heat of the Earth, so they would keep going. And over time, you would see carbon dioxide levels building up higher and higher and higher. It might take a long time because it's just a trickle of CO2 compared to what we're doing today. But over time, you would see carbon dioxide levels rising higher and higher and higher. We think it might have taken about 100,000 parts per million of carbon dioxide, ultimately to melt back the ice. But here's the interesting thing. When the ice started to melt at the end of the snowball, this instability would happen in reverse. The Earth would get much hotter and all the ice would very, very quickly melt. We call this the freeze-fry cycle. You go from one of the coldest climates the Earth ever experienced to one of the hottest climates the Earth ever experienced. Because now the ice is gone, but there's all the CO2 left. But of course, what happens? Well, this chemical reaction starts kicking in like crazy. And over a period of tens of thousands of years, the carbon dioxide is turned into calcium carbonate, buried in the ocean floor, and climate is restored. And so the Snowball Earth story is one of catastrophe, but also of redemption. Right? And in fact, we think that this happened not just once in Earth history, but actually 4 times in Earth history, twice around 2.5 billion years ago, and then twice again between 700 and 600 million years ago. And we think that those changes actually perturbed the atmosphere and the amount of oxygen in the atmosphere in ways that may have actually led to all sorts of biological innovations, including the origin of large multicellular animals. So we might not even be here if it weren't for those Snowball Earth glaciations. Very interesting. So now I want to step back away from the Earth and actually think about our neighboring planets, Venus and Mars. But before we go to either Venus and Mars, we have to talk a little bit about our star, the Sun. So our star is a main sequence star. What that means is that the energy that it emits out to space that essentially keeps the Earth warm is actually driven by fusion reactions of hydrogen turning into helium. Okay, so hydrogen is combining to form helium in the Sun's core, or just at the outer edge of the Sun's core, and that's actually what's giving rise to the high temperature and the emission of all of this visible light that penetrates throughout the solar system. But what's interesting is about 4 billion years ago, when the Sun was relatively new, it was much dimmer. It was probably 30% dimmer than today. We call this the faint young sun. And the reason actually has to do with the evolution of these fusion reactions. I want to show this to you by taking a look inside of the Sun. So we're going to take a look at the core of the Sun, and what you see is that little core. What that is the helium that's the product of these fusion reactions. So hydrogen is being turned into fusion under huge pressure and temperature, and it's slowly building up in the core. So the core is getting larger and larger and larger as more hydrogen is turning into helium. Every main sequence star goes through this evolution, and as that happens, the fusion reactions get closer and closer to the surface of the star, and as a result, the temperature heats up and the star gets brighter. So every main sequence star gets brighter and brighter over time. And this evolution is very important. Now, this chemical reaction we talked about between carbon dioxide and water and rock ultimately has kept the Earth stable over a long period of time. As the sun has gotten brighter and brighter and brighter, the carbon dioxide levels went from being very high to very low, because as the sun got brighter, the chemical reaction sped up, and essentially this thermostat stabilized the Earth's climate. It turns out if we fly to Venus, we discover that it didn't work so well on Venus. Let's take a look at that. So we're going to leave our sun, and we're going to head to Venus, which is, of course, our planet next nearest to the sun from the Earth. Where are we now? This is the part where I have to stay still, otherwise I'll fall over as we fly through space. Okay, here we are. This is the planet Venus. It is not so hospitable to life. The surface temperature on Venus is 462 degrees Celsius. That is pretty steamy. What's interesting is that temperature barely varies around Venus. It's just a few degrees of variation across the whole planet. And a day on Venus is about more than 200 days on the Earth, because it spins very slowly. And so even on the dark side of Venus, it's still 462 degrees Celsius. And the reason is that the atmosphere is incredibly thick, about 90 times thicker than the Earth's atmosphere. And it's composed almost entirely, 97% of the Venus atmosphere is carbon dioxide. Now, what's interesting is you might think that it's so steamy on Venus because it's closer to the sun. And it does get about twice as much solar radiation as the Earth. But it turns out that that's actually not the explanation. If you actually imagine that Venus had the same atmosphere as the Earth, it would actually be colder than the Earth. And the reason is, if you look at Venus, you see how bright it is. Venus reflects so much light back to space that, in fact, even though there's twice as much solar radiation as the Earth because it's closer to the sun, it actually absorbs less than half the solar radiation that the Earth absorbs. So all things being equal, it would actually be colder than the Earth. The reason it's so hot is because it has this thick super greenhouse atmosphere, 90 times thicker than the Earth, composed almost entirely of carbon dioxide, whereas we have an atmosphere that's mostly nitrogen and oxygen with just a mere 410 parts per million today of carbon dioxide. What's interesting is that this may not have always been the case. Remember the story of the faint young sun. So back 4 billion years ago, when the sun was much dimmer, Venus might have looked completely different. Let's imagine that this is the case. Again, scientifically, it's very difficult to test these ideas. Well, field work is very tricky on Venus. But this might have been what Venus looked like 4 billion years ago, with water on the surface and, who knows, maybe even life. Again, that's highly speculative. That's not a scientific fact. But here's what's interesting. As the sun would get brighter, carbon dioxide levels would lower to adjust for the ever-brightening sun. But eventually, carbon dioxide levels would get so low that essentially the thermostat wouldn't work anymore, because eventually you can't get lower than zero, right? So if all of the carbon dioxide went away from the planet, well, at that point, the water would start to heat up. The surface of the planet would heat up because the sun would keep going, and there'd be no more carbon dioxide. And at that point, the oceans would slowly turn to steam and eventually escape the planet's atmosphere, and Venus would lose its water. And so let's watch how that happens. So Venus would lose its water, but once it actually lost its water, the volcanoes would keep going. They don't care. And so carbon dioxide would continue to start to build up now. So first it would actually lose its water, but once the water's gone, this chemical reaction is over. You have CO2, you have rock, but you don't have water. And once you've lost your water, now the carbon dioxide just comes out of volcanoes, and 2 billion years or 3 billion years later, you end up with an ultra-thick atmosphere of carbon dioxide and a super high temperature. Did this happen on Venus? The answer is we really don't know. But there is some evidence that Venus once had water. The heavy isotope of hydrogen, deuterium, is abundant in Venus's atmosphere. And it's a sign that once there was water on the surface of Venus, and the hydrogen escaped, but the heavier isotope of hydrogen, deuterium, was left behind. And so that's some evidence that at least there might have been water once upon a time on Venus. Now, we're going to go to the other neighboring planet, Mars. And this is a little bit like the three bears. Venus is too hot, Mars is too cold. So let's fly to Mars. Again, I'm going to hold on here. Okay, and we're going to get to Mars. Mars is very different than Venus. When we did this in rehearsal last night, we actually flew right through the center of Mars, and it was kind of jarring to everybody. I'm glad that didn't happen. Thank you, Mark. So here is Mars. The surface of Mars is really cold. It's minus 50 degrees Celsius. It's like a snowball Earth, except it's not covered by ice. There are ice caps at the poles. And so there is water ice and carbon dioxide ice at the poles. Mars has carbon dioxide in the atmosphere. Not that much. It's a thin atmosphere relative to the Earth. It's less than 10% of the density of the Earth's atmosphere. But it's mostly carbon dioxide. And there's water on the surface. So what's missing on Mars? Well, just like Venus, in this case, there's actual evidence. Here we are on the surface of Mars. This is the Curiosity rover exploring the surface. And we've now set up a number of missions to Mars with orbiting missions and also rovers that are exploring the Martian surface, looking for evidence of what happened but around 4 billion years ago. Because at that time on Martian history, we have evidence that there was flowing water. That isn't to say it was warm like the Earth. It's not clear there was ever any life on Mars. But it was certainly much warmer because we see geologic evidence for flowing water on the surface. That water seems to be gone now. There's water frozen at the polar ice caps, but it's way too cold to have rivers flowing on Mars. So what happened? Well, again, there's carbon dioxide on Mars. There's water. What's it missing? The answer is it's missing volcanism. Volcanism is the critical thing on both Venus and the Earth that allowed the carbon cycle to continue to work and this thermostat to function. Right? There's plenty of rock, carbon dioxide, but what's missing is that source of carbon dioxide, that source of greenhouse gases. Now, we think that it's possible that around 4 billion years ago, this massive volcanic system, you see that huge volcano there, right in the sort of upper part of Mars? That huge volcanic caldera we call Tharsis. And about 4 billion years ago, Tharsis was erupting. This is like 10% of the surface area of Mars. This is a massive, massive volcano. But Mars is very different than the Earth and Venus. It's about half the diameter. It's a small little planet. And so we think that Mars had huge volcanic eruptions early in its history, but then it went quiet. The internal heat wasn't enough, and it actually cooled so that the internal heat disappeared. And so as a result, the source of greenhouse gases, the source of carbon dioxide that we've had persistently on the Earth and Venus essentially went away. So essentially, Venus lost its water, Mars lost its volcanism, right? Whereas the Earth is just right. We've had consistent volcanism, and we luckily have plenty of water on the surface of the Earth as well. Okay. Let's go back to the Earth now, and I want to just remind you what I said earlier about how the carbon dioxide, about how this carbon dioxide thermostat, this chemical thermostat, isn't a perfect one. It doesn't regulate the temperature to be a particular value. There's lots of variations that are possible. For example, if the amount of carbon dioxide coming out of volcanoes changes for some reason, the Earth would be warmer. And indeed, if this is what the Earth looks like today, if we go back 100 million years, this is what the Earth might have looked like. Now, there's a friend of mine, a colleague who's a professor at the University of Chicago, who actually is a specialist on these kind of reconstructions. And I'm a little embarrassed because what he'll see here, you'll notice right away, is that there are political boundaries on this reconstruction. And let me tell you, 100 million years ago when the dinosaurs lived, the states of the United States of America weren't actually formed yet. But that's okay. That's just for reference. And so I hope everybody will forgive that. What you see is the Cretaceous Earth looked completely different. One of the big things you'll see just looking at the continents, and we're going across the big Pacific right now, so it'll take a second before we get back to the continents. But what you'll see is that large areas of the continents were covered by water. Sea level was about 100 meters higher than today. A lot of that because we had no ice sheets. There was no ice on Antarctica, no ice in Greenland, no ice even on high mountains. The deep ocean was about 10 or 12 degrees warmer than today. Completely different world. There's evidence of plants like palm trees that mostly live in very warm areas, living at very high latitude. And same with crocodiles and dinosaurs, species that are really designed for warm climates, living up at very high latitude near the poles. So it was a completely different world. By the way, I want to emphasize that these warm climates that we've had periodically in Earth history, they'd be perfectly fine for humans. We are quite adaptable as a species. So, this would be a kind of a bad climate for skiing, but other than that, if my friend Dave Rowley's an ice hockey player, that would be a problem in this climate. But other than that, this would be a perfectly good climate for humans. The problem is not that we couldn't survive in a warm world. The problem is that we're heavily adapted to our current world. We and all of the other living things on the planet. And so a lot of the issue of climate change is not that a warm climate is somehow worse than a cold climate. The question is really about the timescale of change and how we are going to transition and adapt, and how all the other plants and animals will actually deal with such a rapid change over just a century or two. Okay, so let's leave the Cretaceous and go back to the Earth. What we're going to do is talk a little bit about the impacts of climate change. What is climate change going to do to our planet? Well, it's obviously going to make things warmer, and that's a problem. The famous heat wave in Chicago was one of the triggers for political concern about climate change in this country. Heat waves, storms. One of the most profound things, though, is the effect of climate change on sea level rise. Now, a lot of sea level rise is driven by just warming the ocean. It turns out that the dominant factor behind sea level rise today is just the thermal expansion of seawater. That is, warmer water actually takes up greater volume. And so as the oceans warm, sea level rises. But what we're worried about in the future is an acceleration of this driven not by just the oceans warming, but actually by the polar ice caps. This is Greenland. Greenland ice sheet is a remarkable thing. It's 3 kilometers high. There's so much ice on Greenland, it's so massive that it actually has its own tidal force that we can measure on the ocean. It actually draws the ocean towards it. It's incredible. If you melted all of Greenland, sea level would rise on average about 7 meters, or 23 feet. This is a massive system that's part of the Earth system, and it's changing rapidly. We actually have an extraordinary satellite called GRACE that actually measures the gravitational field of the Earth. What I want to show you is GRACE data over the last 15 years that actually shows in red and places where ice is being lost, and in blue, places where ice is growing. And what you can see in Greenland is the ice seasonally growing and shrinking, but gradually disappearing. Now, don't worry, there's still plenty of ice on Greenland. The current rate of loss of ice from Greenland, it looks very red and very dark. That is the GRACE observations, but if you actually quantify that, wait, hold off, let's not go to the Antarctica just yet. If you actually quantify that, the rate of sea level rise is only about 0.8 millimeters a year from Greenland. 0.8 millimeters a year, that's not that much. Over 100 years, if it stayed that way, that would only be 8 centimeters. Surely we can adapt to that. Here's the problem. 10 years ago, at the beginning of the GRACE data, that number was only 0.5 millimeter a year. It's accelerated more than 50% just over the 15 years that we've been observing it. And so what people are worried about is a much more dramatic acceleration of the Greenland ice sheet loss. Antarctica is a different story. So let's go take a look at Antarctica. again with the GRACE data. Because Antarctica is so cold, it's a polar continent that's not, Greenland's at high latitudes, but Antarctica is over the pole. It's much colder than Greenland. And that means that warming on Antarctica doesn't necessarily melt the snow. It's so cold that Antarctica could warm up a lot and still the ice would never melt. So what we're seeing on Greenland is surprising with GRACE. We see areas that are clearly melting, but then there are other areas that you'll see in blue where ice is actually accumulating. And that's because warmer temperatures are bringing more snowfall. And so we're seeing places where it's not melting, but it's just actually snowing more, and that's actually building up the Antarctic ice sheet. Overall, Antarctica is losing mass at about a level of equivalent to about 0.5 millimeter of sea level rise per year. But the big question is, how much will this accelerate in the coming century? There's more than 50 meters of sea level rise equivalent on Antarctica. And so if Antarctica suddenly started to dramatically accelerate its ice loss, do we think we could engineer a way out of it? That's what has many of us troubled. Now, again, talking about sea level rise here in Chicago may not be the most relevant thing. It's not that any of you should worry about sea level rise on your houses. At least I hope that we're not going to get to that level. But there are many other impacts of climate change we don't have time to talk about today. Storms. Last year, remember, a hurricane in Houston dropped 50 inches of rain in one storm. 50 inches of rain. When we have 2 inches in Boston, it's a huge flood. I can't even imagine what living through 50 inches of rain in one storm looks like. And of course, a variety of other things. The impact of climate change on agriculture and many other factors. But one of the impacts that is most near and dear to me comes from the fieldwork I've done in coral reefs around the world. We're going to zoom into Australia and take a look at the Great Barrier Reef for a second. This is a picture of what it did look like on the Great Barrier Reef before 2016. Hold on, we're about to go underwater. We're getting there, Mark? Okay. So here we are in a beautiful coral reef. These corals are incredible building blocks for unbelievable biodiversity in the ocean. About a third of marine biodiversity lives in coral reefs. And these corals are actually animals. They're colonial animals. They're colonial animals that are incredibly simple, but they have algae living inside of them. The algae are called zooxanthellae, and they're endosymbionts, and that means that the algae are actually living inside of the coral. The algae are photosynthetic, and so that gives some of the colors you see, and they basically provide some of the food that they create from sunlight. They give that to the coral, and the coral gives them a safe place to live. But it turns out that if the temperatures get too hot, if the temperatures exceed what the corals have experienced historically, for reasons that we don't completely understand biologically, what happens is those zooxanthellae decide to leave. The corals either expel them or the zooxanthellae leave, and the net result is the corals bleach. Now, sometimes they can recover, but many times they die. And this is what a bleached coral reef looks like. In 2016, and then again in 2017, for the first time ever, 2 years in a row, the Great Barrier Reef had an unbelievable bleaching event attributed to record high temperatures measured over much of the coral reef. At this point, 2/3 of the northern part of the Great Barrier Reef is severely damaged. So my recommendation to you as someone who I've had the privilege of diving on coral reefs all over the world, if you haven't, and if you have any desire to, or if you want to take your children to see some of the great coral reefs, do it soon. I have a 10-year-old and a 12-year-old, and I can't wait till they're old enough to be certified for scuba so that I can take them to see some of the things that I've seen, because they're not going to last that much longer. Okay. This is kind of depressing. I apologize for that, but so here we are. What's this experiment that we're doing, and what can we do about it? You know, one of the challenges here is that the driving forces for climate change ultimately are us, people. What I want to show you is a simulation starting in 1950 that shows the population of the Earth. Each of these yellow dots is 1 million people. And so what we're going to do is we're going to look at the changes that have occurred just in the last 60 years. So 1950, there were 2.5 billion people. In 1960, there were already 3 billion people. 1974, 4 billion people. 1986 or 7, 5 billion. 1999, 6 billion. 2010, we passed 7 billion. Today we're at 7.6 billion people. Kind of incredible. And by the way, unfortunately, we're not going to stop at 7.6 billion. From 2018, demographers project that we're going to add probably around 2 billion people. We'll be somewhere between 9 and 10 billion people by mid-century. That's extraordinary. Remember, every one of those people on this planet has the right to the same kind of quality of life that we enjoy. Many of them don't have it, but they certainly have the desire for it. So how do we provide the kind of quality of life that we have today for future generations as the population reaches 10 billion without completely destroying this planet? Well, the answer comes in technology. And there's been a lot of progress. Here we are just a little bit south of here in Indiana. Take a look. You can actually see windmills as far as you can see in every direction. Wind power has come down in price by an incredible amount in the last decade. Today, 35% of the electricity generated in Iowa is from wind. Unfortunately, that's not true for the rest of the country, and Iowa is actually a pretty small state. But it's promising. The price of wind is dropping, and it's actually competitive with electricity from natural gas. The same is true, by the way, for solar. So here we are in a solar panel, a solar farm not too far from here. And you're used to seeing these now. 10 years ago, you didn't see them anywhere, and suddenly they're happening everywhere. In California, they're now about to pass a law. I think it's actually a crazy law, but it's a law requiring every new house to have solar panels on its roof. Now, the good news is the price of solar and wind have come down dramatically. So on a windy day, the Republic of Ireland actually gets more than half of the electricity from wind. That's the good news. The bad news is that we still need electricity often when the sun isn't shining or when the wind isn't blowing. And that's a really big technical problem. What are the solutions? Well, nuclear power is not yet making the kind of advances that solar and wind have. Some people think it will. Batteries are improving, but not quite there yet. Remember, a lot of the fossil fuel we burn is from transportation, and it's going to be really hard to displace gasoline out of our transportation system, and even harder to displace diesel fuel that drives our heavy trucks. So there's progress. Electric vehicles are getting better, but they're still very expensive. We have a ways to go. Ultimately, though, technology is going to have to solve this problem, but here is the challenge. And let's take a look at the Earth again with a slightly different view. This is now the lights of the Earth from space. I think this is kind of beautiful, the night lights of the Earth. And to me, it's both chilling and maybe promising. It's chilling in that it kind of gives you the scale of human appropriation of the Earth system. This is how much impact the humans have now on our planet, clearly visible from space. It gives you a scale of how big our energy systems are that supply all of the energy we use for our lives. It's massive. And rebuilding our energy system without fossil fuels will not only be expensive, but it's going to take a long time because there's only so much stuff we can build every year. On the other hand, we did this. And so maybe it's an existence proof that we can do it again, but even better. I'll tell you a story about Franklin Delano Roosevelt when he was president. In 1941, the Japanese bombed Pearl Harbor, and a month later, he gave the State of the Union address in January of 1942. He promised to build 160,000 airplanes in the next 2 years, 130,000 tanks, anti-aircraft guns, ships, more than the world had ever seen. And many people in the US, in particular in this part of the world, thought he was crazy. The heads of the automobile industry came to Washington and they said, "Mr. President, we can provide 10% of what you ask. But beyond that, you will seriously injure the automobile industry in the US." And he looked at them and he said, "Gentlemen, you don't understand. We will not be building any automobiles in the US." And that's what happened. From 1942 to 1945, we didn't build automobiles in the US. We turned our entire industrial capacity into making ships and airplanes and tanks and anti-aircraft guns and other military hardware, and we exceeded the goals that FDR had set. Now that's political will. We're obviously far short of that today on this problem. The question is, how hot does the Earth have to get before that kind of political will is generated? I will note that it's a much more difficult problem than World War II because this isn't just something that one country can do. Ultimately, this is a global problem. It's a collective action problem that requires cooperation from every country in the world. So where are we heading? Let's take a look at, wait, hold on, can we go back? We're going to go to 2018. Okay, so here we are starting in 2018, again with a rather rosy Earth. Okay, going backwards. 2019, okay, that's next year. So very close to 410, maybe 412 parts per million. As I said, by 2050, we're going to be at 500 parts per million. Let's start going forward. By 2100, we'll probably be somewhere between 600 and 700 parts per million. And that's even with all of the interventions we're thinking of. Now, it's very unlikely that the world is going to, at this point, given what we're doing today, going to stop at 2100. Fossil fuels, are we going to really stop using oil for gasoline for automobiles? Maybe. What about for jet airplanes? So it's going to probably continue out to 2200, where we'll be somewhere around 900 or 1,000 parts per million. And now the planet's getting really hot. The good news is if we were actually to go cold turkey at 2200 and stop burning fossil fuels altogether, a lot of that carbon dioxide would start mixing into the oceans and dissolving into the oceans. So as the oceans mixed out from 2200 out to about 4000 AD, the next 2,000 years, maybe about a half of that carbon dioxide would disappear. So we'd be down to maybe only 500 or 600 parts per million. If we waited another 6,000 years out to 10,000 AD, more carbon dioxide would disappear into the oceans because of other chemical reactions that occur. And so now we're getting down to levels that are closer to what they are today. They're somewhere between 450 and 500 parts per million. But to restore the Earth back to what it was before the Industrial Revolution, well, that requires this chemical thermostat. And that time scale is probably 100,000 years. So over the next 100,000 years, carbon dioxide would slowly drift back to something close to the pre-industrial level of 280 parts per million. I think the important thing to realize here is that the decisions we're making today, in terms of what energy we use, have implications not just for our children or our grandchildren, but the carbon dioxide we're putting in the air today is going to be there for tens of thousands of years. I don't even know how to think about that from any kind of political or ethical perspective. We don't think about those timescales normally. Even as a geologist, I don't think about the implications of my behavior for 20,000 years. But that's the experiment we're doing. Now, what happens if we don't do enough? Remember that, by the way, even if we were to stop using fossil fuels immediately, there's a lot of actually warming that would continue to happen just because the oceans are continuing to warm up, and that would actually drive another probably degree or two of warming beyond what we've already experienced. So we're really in a difficult situation. Some scientists have actually talked about an engineering solution. Could we actually engineer the entire climate of the Earth? It's a terrifying idea, but I want to talk with you about it briefly. Here's how it would work. Volcanoes, when they erupt, really big volcanoes, they sometimes inject into the upper atmosphere, the stratosphere, sulfur dioxide that turns into sulfate aerosols. And these sulfate aerosols are particles that essentially reflect sunlight back to space. It's like a sunshade on the Earth. And this happens naturally. Well, the idea is that we could actually take artificial particles that reflect sunlight and put them high up in the atmosphere near the equator. And the winds at the upper atmosphere and the stratosphere would naturally mix them from the equator towards higher latitudes. It mixes very quickly along the equator, but gradually they would actually slowly mix towards higher latitudes. And you would essentially have a reflective shield. It would reduce the incoming solar radiation by just a few percent. So it's not like it would suddenly become dark outside. It would just be a 2 or 3% drop in how much sunshine came in. And that would essentially compensate, some people think, for the higher levels of carbon dioxide. Now, this is a deadly serious idea. Some people think it's unethical to even think about this. I actually think it's essential. I think scientists have an obligation to think hard about this, especially all of the ways that it could go wrong, because I suspect that sometime this century, some country is going to try to do this. You know, we usually think that, oh, this is going to be done by us. We're going to be in control. But how would you feel if China decided to do this on their own? It's remarkably cheap. It's probably only a few $1 billion a year. So there are many countries that could afford to do this. How would you feel if India decided to do this unilaterally? And they controlled the thermostat of the climate for the whole world, for every living thing on the planet. I think scientists need to understand all of the ways that this could go wrong, but I actually suspect that, again, somebody will try to do this century. I think there are big questions that we need to understand about how it works and what might go wrong. Okay, so let's step back now and think about our planet again. We see the lights of our planet, and ultimately here we are back at this coal plant in Illinois. Let's take our red goggles off for a second and turn it back to where it was. So now the CO2 is invisible again. This is the planetary experiment we're doing right now. Ultimately, though, the choice is ours. Will we actually act together, invest in the technology needed to turn this sort of coal plant off and ultimately change the way we build our energy systems? Well, we're making progress, but not fast enough. This is something that all of us are going to have to deal with, and especially the young people in this room even more. We're already seeing the effects of climate change, and they'll only get more severe. Let's step back now and think again about the Earth system. I hope you've appreciated, relative to Mars and Venus, that the Earth is remarkably special. Its climate has evolved in a way that has sustained life for 4 billion years. And we've seen huge climate changes, although never quite as fast as what we're experiencing today. We're doing a geological experiment on the planet that really in some ways has never been done. As I said, humans are remarkably adaptable. As a species, we will probably be fine. But as individuals, many of us will suffer. And of course, natural ecosystems are going to suffer even more. So the choices we make over the next 2 decades will really greatly determine how the story of the Earth system plays out over the next many thousands of years. I think there's a lot of hope, but we have to admit that there's a grand challenge ahead of us. And it's time to get busy. Okay, thank you very much. We'll stop there and take questions.
Great. Hello, I'm Andrew Johnson. I'm the Vice President here at the Adler for Astronomy and Collections. We do have time to take some questions, both from the crowd here in Chicago, but also from our remote venues. So if you're at one of those remote venues and listening to me right now, please send in those questions. Before we do that, though, I just want to provide a couple of examples of ways that you can actually learn more and you can explore and actually take part in science. Here at the Adler, we're very proud to help bring the world the Zooniverse, which is the world's largest platform for citizen science, which includes many projects that are actually related to climate science. You can actually log in, and it's on the screen there on the left right there. One of those projects is called Floating Forests. It's a project where you can log in online and look at images from Earth orbiting satellites to help map changes in plant life in the oceans, to understand connections between that plant life and changes in the atmosphere as the temperature changes. On the other side of the screen, there's actually a link to a survey that you're all welcome to register what you think of the program tonight, so we can help improve the program moving forward. There's the link right there. That's bit.ly/Kavli4, Kavli4. So please check that out and give us your thoughts. Here in Chicago, we hope you'll come back here to the Adler Planetarium. Among other things, one example of something we're doing this summer is our Summer Film Fest, which includes a sample. It's a selection of different planetarium shows from around the country and around the world that we'll be showing here this summer. So with that, we'll start by taking a couple of questions. If you have a question here in Chicago, please raise your hand and wait for me to come with you to the microphone so that everybody can hear you. Here I come.
Amongst the geoengineering possibilities, you didn't mention carbon sequestration, which I think is much more locally focused and without so many potential bad side effects. Could you address that briefly?
Sure. The question of carbon sequestration is really a way of either using fossil fuels and preventing the accumulation of carbon dioxide in the atmosphere by burying the carbon underground, or by actually taking carbon dioxide out of the atmosphere. For example, if you either chemically capture it or you, for example, burn plants and turn them into CO2 and then sequester that carbon dioxide. That also works as a negative sink for CO2, so it sucks up CO2 out of the atmosphere. The problem with carbon sequestration, it's really an important thing to do. And it may be really important in the future, especially as our will to reduce emissions continues. There are certain chemical factories that are very difficult to decarbonize otherwise. And so carbon sequestration is going to be a very important play an important role in our new energy economy. The problem is it's slow and it's expensive. Today we're putting 40 billion tons of CO2 per year into the atmosphere. And so even doing carbon sequestration at a few million tons a year requires a huge industrial activity. So the scale of carbon sequestration, at least today, seems hard to imagine that it would ever be big enough to make a very quick difference. Even if it could be 40 billion tons a year, it would take 100 years to change the atmosphere. So the difference with the kind of geoengineering that I was talking about is that it actually can change the climate instantly. With that speed, of course, comes appropriate risks. And so that's the challenge.
All right, we've got a question over here.
Hello there. My question is, we've gone through all this, the carbon evolution, and we have population growth. So with that, we have the problem of producing enough food product, and conversely, we also are manufacturing garbage at an unprecedented rate. Could you address those problems?
So solving all the world's problems in one evening. Wow. the answer is, so most scientists who have thought about this problem think that because of the increase in population, but even more important than the increase in population, turns out to be the increase in wealth. Turns out as people get richer, they like to eat better. That's not so unreasonable. And so the increase in food demand is actually not coming so much from the extra 3 billion people. It's the people who are already here who are getting richer and prefer to have more meat in their diet. Remember that when you eat beef or chicken or pork, it requires a lot more grain to feed those animals than just eating the grain itself. It's a good argument for being a vegetarian. But the fact is, most of the world doesn't want to be a vegetarian. A lot of the world wants to eat more meat as they get richer. And that's creating huge strain on the food production systems. So most people think that by mid-century, we'll need to probably double the amount of food production globally. Now, it turns out that if you actually think about this problem in detail, there's a number of ways to solve it that are more so. First of all, there's big areas of the world, especially in Africa and in South America, where agricultural productivity remains much, much lower than in a place like the US. So there's an opportunity to improve agricultural methods and increase the yields dramatically in other places. But the other point is that we actually waste a lot of food. Here in the US, more than half of the food we actually grow, we throw out. So that's the garbage side of your equation. And so, frankly, economics has a good solution for that. If food were more expensive, we'd probably waste less of it. So I think some of that is just going to work itself out.
All right, we got a question at one of our remote venues.
Yeah, we'll start with a question we have from our friends in Fort Collins, Colorado. They're wondering if you could speak to the role that the Earth's magnetic field plays to the atmosphere and climate.
It's a very interesting question. So the Earth's magnetic field is driven by the movement of molten iron in the outer core of the Earth. And it plays an important role in the atmosphere in terms of reflecting cosmic radiation. So if we didn't actually have a magnetic field, it's possible that many of us would be vulnerable to very harmful radiation that would come from outer space. But luckily, we do have a magnetic field, and that's partly why life has prospered on Earth for so long. In terms of climate, the Earth's magnetic field has very subtle effects that are completely overwhelmed by the kind of change in carbon dioxide. So the magnetic field of the Earth doesn't really play a role in affecting the Earth's climate on these kind of timescales.
Another remote question.
So if the Earth's magnetic field does not play a role, our friends in the Como Planetarium in Minnesota are wondering, does methane figure into the future of climate change?
Absolutely. So I've focused today on carbon dioxide, which is the main greenhouse gas. There are other greenhouse gases, methane, nitrous oxide, a number of others. Some different types of fluorocarbons, for example, are very powerful greenhouse gases. Methane is one of the more important ones after carbon dioxide. And the interesting thing about methane is that it has a short lifetime. So it only lasts about 10 years in the atmosphere. It then, by the way, gets oxidized and turns into carbon dioxide. But if you think about this on a kind of 100-year time scale, methane is actually molecule for molecule or pound for pound. It's about 25 times more powerful than carbon dioxide as a greenhouse gas. But there's much, much less of it. So the current concentration of methane in the atmosphere is about 2 parts per million, whereas carbon dioxide is 400 parts per million. So while methane is a very powerful greenhouse gas, carbon dioxide is still the more important one. And the other thing is, because it has a short lifetime, it means that the carbon dioxide is going to continue to accumulate and stay around for thousands or tens of thousands of years, whereas the methane will go away. So frankly, if we focus too much on methane and lose track of carbon dioxide, we're going to miss the big picture.
Want to take another remote question, and then we'll take one
Sure.
from Chicago.
We'll stay in Minnesota. The Rochester Paul Mayo High School at Rochester, Minnesota. They're commenting that the Gulf Stream is slowing down. And what is your assessment of that?
So it's interesting. Some people have talked about this as a big concern, that the ocean currents will be affected by climate change and the Gulf Stream will slow down. I would say that what they're actually talking about is the sinking of water in the North Atlantic and the formation of deep water. And that might indeed slow down. But the effects of that change in the ocean currents on climate are probably have been exaggerated, including by scientists in my community. How many people here saw The Day After Tomorrow when it came out? Number of you. Good. It's total rubbish. It's an awesome movie. I actually appeared with Al Franken at an event in New York City before that, when that movie was released, before he became a senator. And he made a rather crude joke about that movie. He called it climate porn. He said it's the sort of movie that a scientist like Dan would watch in his hotel room, but he'd be too embarrassed to put the name on the bill.
Is that true?
No comment. I actually get great pleasure watching it because it's awesome. You see the tornadoes in Los Angeles blowing buses around and all sorts of amazing things. The reality is, in that movie, it's all driven by a shutdown of the current in the ocean. The reality is that the Gulf Stream is mostly driven by the winds, which are driven by the rotation of the Earth. And that's not going to change.
All right, we had a question here. Actually, here, sorry.
Just a quick diversion back to methane. Are you or your community worried about sudden melting of the permafrost and a quick release of a large amount of methane?
So that's a very good question. So there's a huge amount of carbon stored in peatlands and in soils in the permafrost. But it turns out, there's been a lot of discussion about methane release. Turns out if it came out as methane, that would be the good news, because the real problem is the carbon dioxide. The answer is when you actually melt the permafrost, there's lots of organic matter in those soils, and the bacteria go to town. Right? It's so cold today that they're frozen, they can't eat it. But when it melts, suddenly they go after it and eat it and turn it into carbon dioxide. All of this juicy plant matter that's just been sitting there frozen for hundreds of thousands of years. Most of that's in Siberia, and the reason is that Canada was glaciated, and so all of the organic matter in the soils were scraped away, whereas in Siberia, it's such a big continent that the interior never actually built up a big ice sheet, and so as a result, there's thick, organic-rich soils in the permafrost regions. Now, if conditions were wet, then methane would come out, but it would be probably less than 0.1% of the total amount of carbon that would come out if it actually were dry. And so far worse than methane, if the permafrost melts, and it is already melting, would be the release of carbon dioxide, because much more of it will come out. So ultimately, the answer is, yeah, we do worry about the permafrost. And to give you a perspective on that, there's probably about 1,000 billion tons of carbon stored in the permafrost. That's equivalent to probably all of the fossil fuel that we have burned already and that we're likely to burn in the next 50 or 60 years. So if we sort of lose control of the Earth system and all of that permafrost carbon gets turned to the atmosphere, now we've really lost control, because even if we stop burning fossil fuels, now the Earth is adding carbon dioxide on its own to the atmosphere. Right? That's the kind of feedback that was really scary. And the answer is we don't actually know much about it. Turns out we've done a lot of work in Alaska and in Canada. We really need to do the work in Siberia, and politically that's very difficult right now.
All right, we got a couple more questions remotely.
Related to what you were just talking about from our friends at the Planetarium in Vancouver, a small number of scientists think that we are at the beginning of an ice age, and CO2 is actually slowing down the process. What are your thoughts on that?
Well, I think that's absolutely true. We are at the beginning of an ice age, and it's true that CO2 that we've added from burning fossil fuels is slowing down the process. I think the important thing is to put this in perspective. We are at the start of an ice age that over the next 80,000 years will slowly build up a new ice sheet, had we not ever had the Industrial Revolution. So the ice age was hardly something to be afraid of, because that ice sheet was going to happen over the next 80,000 years. Right? What we've done by raising the atmospheric CO2 already to 410 and likely to something like 7 or 8 or 900 parts per million over the next 2 centuries, that's not only going to prevent the next ice age, it's probably going to deglaciate certainly all of Greenland eventually, and a good chunk of Antarctica. And so it's going to be like resetting the ice age cycle altogether. So we probably won't have another ice age like the last glacial maximum 20,000 years ago for hundreds of thousands of years. So it's true, we were heading into a new ice age, and the burning of fossil fuels has prevented it, but that's not really doing us a favor.
Another question from the Boonshoft Planetarium in Dayton, Ohio. Is water vapor considered a greenhouse gas?
Absolutely. Water vapor in the atmosphere is a very powerful greenhouse gas, and clouds also have other effects that can sometimes warm the climate dramatically. We don't think of water vapor, though, as sort of an independent control on the climate, because it's a little bit like the signal in your stereo. You know, there's an amplifier that essentially amplifies the signal to give you the sound that you hear in your phone or in your stereo or whatever. But it's not actually setting the signal. And the reason is 70% of the Earth's surface is covered with water. So when the Earth warms up, more water goes into the atmosphere, and it gets warmer. That's a positive feedback, but it's not an independent dial. And so carbon dioxide is driving the Earth's climate. Water vapor is amplifying those effects.
And one last question from our remote venues, I think.
Yeah, we have one final site from our relative neighbors down in Peoria, Illinois. They just want to know what you think the most effective thing a single person can do to help solve the climate problem is.
You know, I think it's probably, at this point, the single most important thing is to actually, if you're a kid, talk to your parents about it. If you're a parent, talk to your kids about it. Ultimately, this is a problem that we all have to solve, and I think there's three main ways that we're going to solve it. Number one, we didn't talk about this very much, but we all have to start thinking about preparing for climate change. I think the whole country needs to start thinking about how climate change is going to impact us. Those people in Houston who are at risk of these extreme rain events need to think about that. You need to think about how to protect your family and your community. By the way, in doing so, I suspect a lot of people will realize that this isn't some crazy made-up science, and that they'll actually begin to get concerned and realize that maybe it's good to do the second thing, which is actually make energy choices as we can that favor non-fossil energy. And the third most important thing is ultimately to vote. And it's unfortunate in this country that climate change has become such a partisan issue. In many countries, in Germany and the UK, there's fierce political debates about what to do about climate change. They're not debating about whether it's happening. And that's really something that's special in the United States, and it's unfortunate. I actually hope that over the next decade or two this will change. I don't quite see how we get out of the rut we're in right now, but you know, a few years ago I actually spent time with Eric Cantor, who was the House Majority Leader, the number 2 Republican in the House, and he was extremely conservative. If you recall, every time John Boehner wanted to do something slightly moderate, Eric Cantor pulled him over to the right. And Eric Cantor asked me to come talk to him about what a Republican strategy for climate change would be. And I spent an hour with him and I said, you know, why is it that you want my help? And he said, well, 2 reasons. Number one, we've purged all knowledge of this issue from our party, and so we have nobody to talk to. I said, come on, I'm one of President Obama's advisors. Why do you want me? And he said, well, the other issue is this. He said, under 35 Republicans think we're insane. I thought that was actually very revealing. It says that actually the next generation is going to actually have a big impact on this problem. And I predict maybe not in the next election cycle or even the one after that, but eventually this is going to be an issue that people care about in the ballot box and in the voting booth. And that means that eventually I suspect both parties will actually have different strategies for how to deal with this. And that's going to be a very positive step when we start debating what to do and how to do it and not focusing on whether it's real or not.
Great, thanks very much. Well, with that, if you're here physically with us in Chicago, I'd like to welcome you to share thoughts with each other and with Daniel Schrag out in our welcome gallery as you're exiting. But with that, I'd like to once again thank the Kavli Foundation for their support, thank Dan Schrag for this wonderful journey, and thank all of you for being with us this evening. Take care.